This is a video for MEI Core Pure Mathematics, second order differential equations 3, modeling with second order differential equations, 3.6 simultaneous differential equations, plotting and interpreting solutions. In a separate video, we've looked at this pair of simultaneous differential equations, one involving dx by dt and the other involving dy by dt, with this set of initial conditions, x is 1, y is 3, when t equals 0. And that's given us this pair of equations that are the particular solution to this. X is 2 minus e to the 2t, and y is 2 plus e to the 2t. However, from those equations, what can we tell about the behavior of x and y? To look at the behavior of x and y, it's useful to look at the solution curves. So if we think about a plot here, where this is the t-axis, we'll look at what happens to the values for x and y against t. When t equals 0, x is equal to 1. We actually know that from the initial conditions, but it's confirmed here. E to the 0 is 1, so we get 2 minus 1, which is 1. We can also think about x being equal to 0. You see, e to the 2t is going to get larger as t gets larger, which means at some point this thing is going to go through 0. And in fact, that will be when e to the 2t is equal to 2, which is when t is equal to a half log 2. And that's around about 0.35. The other thing to think about is what happens for large t. Well, as t tends to infinity, this thing is going to become very large. So x is going to go towards minus infinity, but more importantly, it's going to behave like minus e to the 2t. So x will tend to minus infinity, but it's actually behaving like minus e to the 2t. And so if we put these things together, it's going to start around here at 1. It's going to drop through the axis at some point, and it's going to head off down here somewhere. And that's a nice exponential curve, something like that. Looking at y, and a similar idea, t equals 0, y is equal to 3. Again, we can get it from this equation, but we also know it from the initial conditions. We also know that if t is greater than or equal to 0, then e to the 2t is greater than or equal to 1. And so y is greater than or equal to 3. What happens as t tends to infinity? Well, this thing is just going to get very large, and in fact y will also tend to infinity, and it starts behaving like e to the 2t as it gets bigger and bigger because the 2 is relatively insignificant. So for y, it's going to start around here at 3, and it's going to stretch off up this way. So y is going to start from here, and it will pretty much mirror what's happening with x. There's a somewhat neater plot of that for you, so you can see that y starts at 3 and is increasing exponentially with time. That's the red curve. And the blue curve, x, it starts at 1 and it drops through at around 0.35 here. Starts at 1 and it decreases exponentially with time. So what about the behavior of x against y? If we think of this as a pair of parametric equations with parameter t, so we've got x is some function of t and y is some function of t, then if I add x and y together, x plus y is going to be 2 minus e to the 2t plus 2 plus e to the 2t. Those bits are going to go, giving me just x plus y is equal to 4. The other thing I know is that if t is equal to 0, then it goes through the point 1, 3. So I can now plot that on a pair of axes for x and y, and it'll start at this point here, that's 1, that's 3, and it'll go that way, like that. And there's a neater version of that for you. Again, confirmation that x plus y equals 4, so it's going to be a straight line. And this point down here, when t equals 0, is the point 1, 3. And it's x plus y equals 4, which extends this way up the graph. There's a dynamic plot of that with a slider to allow me to alter the value of the parameter t. So as I shift t up and down, you'll see the red point move up and down that line. So that's down at t equals 0. And then as it extends on up the line, this slider goes up as far as 2. It'll take me up to the other end of that line, but obviously t could continue on further than that. So in summary then, when we're looking at the solution curves, it's useful to look at the individual curves, both for x against t and y against t, and also to try and establish a relationship between x and y, accepting that the equations we've got are parametric equations for x and y in terms of parameter t. So we also want to look at x against y. That was the final video in the sequence Second Order Differential Equations 3, Modelling with Second Order Differential Equations.